So let's review what happens if we have a container of a fluid. So let's show a container of a fluid, and it is full of a fluid. Let's say this whole volume is full of a fluid. So let's say it looks like this, a barrel, and let's review the difference in pressure in this barrel according to the depth. All right. So let's say that we have a fluid of some sort of material property that we would know of inside here. And there's the pressure of this fluid is different depending on its depth, because each little piece of volume of this fluid, here's a little volume of this fluid, each little volume of this fluid has mass, right? And each little volume of mass gets acted upon by gravity. So here's a little volume, dV, right? Small amount of volume. At its center of mass, gravity acts upon it and makes a force due to gravity. And there's lots and lots of little masses in here, right? So if I then take a look at the effect of this mass sitting, all the mass sitting at this height versus all the mass sitting at this height, then there is actually a column of fluid. There's a smaller column of fluid here that has mass. So the mass times force of gravity of that would be less than the mass times force of gravity of this column of fluid. So a greater force would act here than it would here. So we'll label this naught. This is position naught, and this is position 1. And everything that sat before position naught, or before this plane naught, or the initial plane, was all of the mass that sat up there with gravity acting upon it. All of the mass with gravity acting upon it. And that's the force caused by all of that, F naught. And that force, F naught, is equal to the pressure of that fluid times the cross-sectional area, A naught. And that comes from our formula, the relationship. Pressure is always equal to the force over the cross-sectional area that it is acting upon. So therefore, P naught equals force naught over A naught. And then if we look at this second cross-sectional area, then of course it has this giant column of fluid on it, which is going to create a larger force at plane 1. And that would be governed by force at 1 is pressure at 1 times cross-sectional area at 1. But what we can notice about the cross-sectional areas is the area at naught is the same as the area at 1. So really, we could just call those both A, yes? So they're the same area A. So we have this equation, P equals F over A, or P at 1 is the force at 1 over A at 1, but A at 0 equals A at 1. We can call them both A, right? So if we set them equal to each other, well, they're not entirely equal to each other. So we would have to determine what the pressure change is from one to the other. So if we remember that the amount of pressure from any given volume of fluid, the pressure change from any given volume of fluid is equal to pressure change is equal to that force due to gravity. So the pressure change is force due to gravity, right? Over cross-sectional area A. And the force due to gravity is mass times acceleration due to gravity. That's a force over A. And how do we derive this? We said that, well, we remembered that density is mass per unit volume. So then mass would be density times unit volume. I'm just trying to derive rho g h, because we know that change in pressure is equal to rho g h. I'm just trying to demonstrate why change in pressure is rho g h, rather than just having that memorized. So if I substitute in m here for rho times volume, I would get rho, density times volume times acceleration due to gravity over area. But volume and area relate. But volume is equal to height, right? If this is height h, then it's height times area is volume, right? Cross-sectional area times height. Cross-sectional area times height. Volume of a cylinder. Area times height. So let me substitute that in. I will get the density times height times area times acceleration due to gravity from my force of gravity over cross-sectional area. So now I'm at a point where the areas can cancel out, and we've just illustrated or proven that the change in pressure is rho g h. So pressure difference according to depth is P1 is equal to P at naught plus rho g h. Rho g h being the difference in the pressure. P1 equals P naught plus delta P. So if we remember how to apply that, what we would do is we would say how much more water pressure is there at depth at 1,500 meters below the ocean surface if the density is this, how much more water pressure, then the answer would just be the change in water pressure, or the amount more would just be rho g h. So that would be the density of water 1026 kilogram per meters cubed, times acceleration due to gravity 9.81 meters per second squared, times 1,500 meters is the depth. So meters and meters would cross out, and we'd have we'd have 1 meter on the bottom, and we would end up in pascals if we were to compute that. So this is a great practice question for the change in pressure equals rho GH. And the type of question this is, remember we talked about statics and dynamics, the type of pressure, the type of question this is in fluids is a statics. This is a statics problem, classic statics problem, and a good one to review.